The subject of our research is generating training data for word-sense disambiguation in Russia. Word-sense disambiguation is a key task in semantic-oriented applications, such as semantic text analysis or semantic information retrieval. It is used in knowledge graphs or lexical semantic resources. To achieve high performance, supervised word-sense disambiguation algorithms require large, sense-annotated datasets. The annotation of such corpora demands considerable time and human resources. That is why supervised machine learning approaches suffer from a knowledge acquisition bottleneck. Automatic generation and labeling of trained collections can help to tackle this problem. In our research, we use the Monosemous relatives method to automatically generate and label training collections. Monosemous relatives are those unambiguous words or word phrases that are connected to the target ambiguous word through some semantic relation. Monosemous relatives approach is based on the substitution. We find the text in which such relative is used, substitute this word with the target polysemous word, and label this context with the sense of the monosemous relative. Usually, semantic graphs such as RuWordNet are used as a source for such relatives. In our research, we exploited Russian thesaurus RuWordNet to extract monosemous relatives. In the examples below, we present some of the monosemous relatives for two senses of polysemous word doctor. However, this method has some drawbacks. Some senses of target words may not have monosemous relatives. Let me briefly describe the main parts of our report. First, we are going to describe the data that we use in our research. That is, RuWordNet, thesaurus, and different corpora. Second, we will tell you about the principal features of our algorithm, distance to monosemous relatives, concept of a synsec nest, and similarity scores. Next, we will present step-by-step description of the monosemous relative selection and ranking algorithm. Then we will overview our methods of compiling training collections. Following this, we will demonstrate the results of our experiments with the different training collections and contextualized word embeddings. And finally, we will show the additional findings concerning the distance to monosemous relatives. In our research, as an underlying semantic network, we exploit Russian thesaurus RuWordNet. It is a semantic network for Russian that has WordNet-like structure. There are 63,014 monosemous and 5,892 polysemous nouns in RuWordNet. This resource was used to extract various semantic relations between a target sense of a polysemous word and all the words connected to it. The graph was also used to measure the distance between the target word and its relatives. The sense inventory was taken from this resource. Now, let us turn to the datasets used in our research. As a reference corpus, we utilized a news corpus that consists of 1 million news articles harvested from various news sources. The corpus consists of 24.2 million sentences and 1.4 million of unique lemmas. For evaluation of our algorithm of trained data generation, we used 3 distinct RuSe18 datasets for Russian. From these datasets, we have taken only those words and senses which have one-to-one correspondence with senses in RuWordNet. So, we compiled a test dataset that consists of the context for 30 target ambiguous word nouns, each having 2 different senses. For convenience, we will call this test dataset RuWordNet. We also created a small training dataset that consists of the word sense definitions and examples of uses from Ozhigov dictionary for every target polysemous word. Each sense of an ambiguous word has 1 definition and between 1 and 3 usage examples. This training data is utilized to train a baseline solution for the word sense disambiguation task. In different works, synonyms, hypernyms are used as monosemous relatives. They are located very close to the target polysemous word in a semantic graph, which makes them more reliable relatives. However, as we have already said, there may not be enough monosemous relatives for all the senses of a polysemous word on such a close distance. The central idea of our method is that a training collection can be built not only with the direct relations like synonymy, hyperonymy, and hyponymy, but also with far more distant words such as cohyponyms, two steps or even more hyponyms and hypernyms. For example, most contexts for the word krona in the sense krona currency match the context of the other words denoting currency like английский фунт, pound sterling, as they have common hypernym valuta, currency. So the advantage of our approach is that we find a lot more monosemous relatives for target senses. But the disadvantage is that we need to score all the relatives that we find because their contexts may not suit as trained samples. To measure the suitability of a monosemous candidate to display target sense of a polysemous word, we exploit a notion of a synseth nest. The synseth nest consists of the synonyms to a target sense and all the words from directly related synseths within 2 steps from a target word. In the following example, we present a fragment of the synseth net for a word taxa in the sense dog. Another important part in our selection algorithm is the similarity score. We utilize similarity scores between a candidate monosemous relative and a synseth nest to evaluate how well this candidate can represent the sense of an ambiguous word. Moreover, we check similarity scores to the synseth nest for every monosemous relative, because a word described as a monosemous in the thesaurus can actually have polysemous usage in a corpus. For example, Russian word iriska, toffee, can also denote a nickname of Everton Football Club, the Toffees. Thus, the usage of candidate monosemous relatives in the source corpus should be further checked. Now, let us turn to our algorithm itself. The selection and ranking method consists of the following steps. We extract all the candidate monosemous relatives within 4 steps from a target polysemous word sense. Then we compile the synseth nest. For each candidate monosemous relative, we find 100 most similar words according to Bottleneck model trained on a news corpus. Next, we intersect these top 100 words with the words included in the synseth nest. The final weight of the synseth in the synseth nest is determined by the maximum weight among the words representing the synseth in the intersection. The total score of the monosemous candidate is the sum of the weights of all synseths from the synseth nest. Thus, the final weight of the candidate can be defined as follows. The formula is given at the bottom of the slide. Our method implies that more scores are assigned to those candidates that resemble a greater number of synseth from the synseth nest. The following fragment of list of monosemous relatives with respective similarity scores, which are given in brackets, was obtained for the noun gvozdika and its 2 senses. We can see that all monosemous relatives are sorted by the weight they obtained. The higher rated monosemous relatives are supposed to better represent the sense of the target word, and so their contexts of use are best suited as training examples in the word sense disambiguation task. Well, once we have selected the monosemous candidates, we can extract from the corpus the context in which they occur. Then, we substitute the monosemous relatives with the target ambiguous word in this text and add this text to the training collection. The news corpus was used to extract the context with monosemous relatives found by the proposed algorithm. In our research, we implemented 2 ways of creating training collections based on monosemous relatives rating. We compiled the first collection only with the monosemous relative from the top of the candidate rating. We wanted to obtain 1,000 examples for each of the target words. For simplicity, we call this collection Corpus 1000 because we obtained exactly 1,000 examples for each sense. As for the second collection, the training examples for the target ambiguous words were collected with the help of all respective unambiguous relatives with non-zero weight. The number of extracted contexts per a monosemous candidate is in direct proportion to its weight. Accordingly, we named this collection a balanced one because we used all the respective monosemous relatives. We conducted several experiments to determine whether our text collection can be used as a training dataset for a word-sense disambiguation model. In our research, we used Conner's neighbor classification algorithm based on the contextualized word embeddings Elmo and Bird. In our experiments, we exploited two distinct Elmo models. The one trained by Deep Pavlov on Russian WMT in use, and the other is RuWordNet's lemmatized Elmo model trained on Taiga corpus. From the first model, we extracted a vector for a whole sentence with a target word. From the second one, we extracted a single vector for the target ambiguous word. We used two BERT models, BERT-based multilingual case released by Google Research and RuBERT by Deep Pavlov. To extract BERT contextual representations, we concatenated the representations from the top four hidden layers. This table demonstrates the results obtained by different types of contextualized word embeddings in training collections and model parameters. As it can be seen, all the systems surpassed the quality level of the baseline solution trained on the dataset of the dictionary definitions and usage examples. The algorithm based on Elmo pre-trained embeddings by RuWordNet outperformed all other models, achieving 0.821 F1 score. The second best model is the RuWordNet by Deep Pavlov, followed by Elmo model by Deep Pavlov. The lowest F1 score belongs to multilingual Bird. As for the difference in F1 scores between the Corpus 1000 and the Balance collection, we can observe the minor performance drop for the Corpus 1000 for all the models except for the RuWordNet model. Corpus 1000 does not include all possible monosemous relatives, so it lacks contextual diversity. The Balance collection, on the contrary, is more representative with regard to the variety of contexts. All those results are summed up on this slide. And now to our additional findings. Only 20 out of 30 words from our dataset have monosemous relatives for all their senses connected to a target word with direct relations like synonymy, hyponymy, hypernymy, which means that our proposed expansion of path is very useful. We evaluated the results of word-sense disambiguation for these particular 20 words using only close-related monosemous relatives and the relatives linked via distant paths that we used before. For evaluation here, we used RuWordNet's Elmo model. We found that the best results are quite similar, 0.841 for direct relatives and 0.835 for all the proposed relatives in our method. Despite the similarly better performance, our selection method ensures wider coverage of monosemous relatives. Now to the conclusion. The issue that we address in this article is the lack of sense-annotated training data for supervised word-sense disambiguation systems in Russia. In this report, we have described our algorithm of automatic collection and annotation of training data for the Russian language. The main contribution of the research is that we have considered in the selection algorithm a wide range of monosemous relative types. We also utilized the metric based on a cosine similarity to determine the most appropriate monosemous relatives to be added to the training collection. In order to evaluate the training collections, we applied Nearest Neighbor classifier to the contextualized word embeddings and measured its performance on the RuWordNet test dataset. The best result was obtained with Rus Victoria's Elmo model and amounted to 0.821 F1 score. So, thank you for your attention.